can see the PowerPoint, right? Hello? Did you see the PowerPoint? Hello? Did you response? Anyone? If you see the PowerPoint, then give me the response.
Yes, sir.
Yes.
Okay. We will apply boundary between point 2 and point 1. Point 1 is just below his thumb, right over here. Okay. Then we'll figure out the height of the water. Now, you see, you figure out the data for point. For point 2, what is the P2? Pressure will be atmospheric pressure, right? If you figure out the gas pressure, then in that case, P2 you can assume equal to 0. What will be the V2? Velocity of water at point 2. Velocity is 0 because water is moving upward with the high velocity due to the gravitational action. Velocity gradually reduce, right? Then at one point, velocity is 0. Then water will fall down. So V2 is 0. If I think this is my reference point, then this much height is the Z2. That they'd like to know. That Z2 equal to how much? And at point 1, just below his thumb, what is the velocity? Just below his thumb? 0. Because velocity of water coming out right over here, but just below his thumb, right this point, velocity is 0. So we'll say V1 equal to 0. And what is the P1? P1 equal to 400 kilopascal. So you can say 400 into 1000 Pascal, right? And what is the Z1? This is our reference line. So Z1 will be 0. Now, you put in the boundary equation, you'll get the Z2. Okay, very simple. Now, this problem is saying water flows under a sluice gate is flowing along this direction. You can move this gate upward or downward to close the gate. Okay, it's a water flow under a sluice gate on a horizontal bed at inlet to a flume. That means going some kind of creek or lake. Upstream from the gate, water depth is this much meter from here to here, right over here. And speed is negligible. But at the top surface of the speed is not that much, you can neglect. At the Vana contracta, downstream from the gate, flow streamline or straight, and depth is this much meter right over here. Now this is one term is coming. What is Vana contracta? Vana contracta means if you look carefully, say when you're taking shower, you open your water tap in full, then you see water is coming down. Then it's spreading fluid, right? But you will see it coming like that. So this is your mouth of your water tap. It's coming down. Then some stage you see diameter of the water right over here, little bit shrink. Then it gradually spreading. So this portion is called Vana contracta. So right over here, water flowing under the gate with high speed. So right over is the height is this much, right? Gradually height is decreasing, then it will might increasing again. Okay, so this portion right over here, this is called Vana contracta. So at this point, the depth of water right over here is 0.051. That is saying, determine flow speed at the downstream. Flow speed right over here, how much the flow speed from the gate, and discharge in cubic meter per second per meter width, and how much volume of water is passing through the gate. That you need to figure out. So you see, if we take 2 points, point 1, the top surface of the water front of the gate, and point 2, just after the gate, also at the top surface. Then for point 1, how much the velocity? Velocity almost 0. What happens? If you make a dam, then water is constantly coming from this side. So this height is not changed that much, remain almost constant. But water is not coming, in that case, this height will be gradually down. And flow velocity will gradually decrease, reduce, right? So this level, normally in hydroelectric electricity, you have Kaptai bath, right? And dam. You see their height, they keep the constant. If you don't keep the constant, then energy of the fluid coming out through the gate will not be constant. It will change with time. That's why this height, if you keep constant, then at the top surface, that means water velocity is 0. So V1 0. What is the pressure at V1? Pressure at V1, atmospheric pressure. And Z1, if this is the reference line, so you'll get the Z1, 0.46 meter. Now at point 2, what is the pressure? Same thing, atmospheric pressure. This is not even nothing else, only atmospheric pressure. V2, that we need to figure out. They want to know flow speed. That means V2. And what will be the Z2? 0.051. So you have V2, that is called flow speed, they like to know. And also they like to know the discharge, Q. So Q equal to area into velocity. So if you know the area of the sluice gate, then you can figure out the Q. This sluice gate is showing like a 2D view, right? Front view, but it is actually like that. That means water is getting out through this S. So if you know the width, right over depth is no 1051. If you know the width, then you can figure out the Q. Q equal to area of the gate into velocity. So let's see how we can solve it. Okay. So this is our reference line, right, along this point. Okay. And we need to apply this Bernoulli's equation. So at first, you figure out the data. We can say atmospheric pressure is 0 because we are considering the gas pressure. Okay. So P1 pressure at point 1. This is point 1. This is point 2. So at P1 pressure is atmospheric pressure. Velocity 0. Or with the Z1 0.46, right over to 0.46. And also P2 will be atmospheric pressure right over here. Even if you're not thinking that P atmospheric pressure equal to 0, you can keep the P atmospheric pressure. Then what will be happening? This will be P atmospheric pressure, this will be P atmospheric pressure. Both will be out, right? And Z1, we know Z1 is given over 0.0. I'm sorry, 0.046, but Z2 is 0.051. They need to know density of the water because P by gamma. Okay, so density of water is rho Then we figure out the value of the gamma. Now we put all the value in the equation. You put all the value of the equation, you see P1 0, this one 0, Z1 value we have, Z2 we know, so we can easily figure out the value of V2. So V2 is coming this much. That means this much meter per second. Now, how will get the value of the Q? Q equal to area into velocity. And what is our area? W into H, right? H is the height of the opening, and width is the how much the width of the gate. So Q equal to WH into V2. Now you see the width, the W is not given, but H is given. What is our H? Right over here. H is the right over here, the height of the gate right over here, 0.051. This height. This is the height. But along this direction, that means width of the gate, we don't know how much the width. So water is coming out through this opening, right? Through this opening. So if you know this area, that means opening area, through the area water is coming out. We can figure out the Q, because Q equal to area into P. So what is the area? W into H into V. What is my H in that case? H is 0.051. V, we already figure out the V, right? But W is not given. How did it go? You just bring W, what is the unit of Q? Meter cube, right? So in the bottom of Q, you bring W the left side. So you are getting H into V. So Q by W, this unit will be meter cube per second, this unit of Q, per width of the gate. So meter cube per second by M. This will be your discharge through the gate. So you see right over here, we can send Q, we got this much. Okay. So Q equal to H means Z2, right? 105 into P. You multiply, you get this the unit Q. This Q is meter cube per second, W equal to M. So you divide it. In right hand side, you will get meter cube square per second. That means actually meter cube per second. Okay. So very easy. Any questions so far? Any question? No?
No, sir.
Okay. So we can keep it here.